Welcome to lecture 27. This is week 6 and we are talking about optimization of unconstrained multivariable functions and we are talking about direct search methods. So, today we will introduce a very popular search method, direct search method for multivariable functions, which is known as simplex method. So, before that we will also talk about unidirectional search and we will also briefly talk about the structure of a general search algorithm for multivariable optimization. So, if we have to minimize a multivariable function, the most iterative procedure will follow the general sequence. First, you will choose a search direction and then you will minimize in the chosen search direction to get a new point. So, if the chosen search direction is S at kth iteration, then we minimize in the direction of S to get the next value of the decision variables at kth plus 1th iteration as x k plus 1 equal to x k plus del x k, where del x k is the increment. So, you must specify initial guess or the starting vector and termination criteria. Now, there are several algorithms. These algorithms differ in two aspects. First, how to go from kth iteration to k plus 1th iteration, that means how to get this increment delta x k. So, how do I change the values of the decision variable at kth iteration to get the values of the decision variables at k plus 1th iteration. Note that these are the trial values of the decision variables, and when convergence is achieved, you get the optimal solution or maybe you are very close to the optimal solution. So, the various optimization algorithms differ on how to generate the new trial values for the decision variables at every iteration, and also they may differ on termination criteria. So, we can present the algorithms for general search technique as follows. Let x k be the current estimate of the optimal solution x star. So, step 1, I test for convergence. If conditions are satisfied, I stop because I have already reached optimal. So, the solution is x k. Next, step 2, compute a non-zero vector d k, which is the search direction. Step 3, compute the step length alpha k greater than 0 such that f of x k plus alpha k d k is less than f of x k. That means, the d k is the direction in which the function value is decreasing, it is a descent direction. So, update the estimate for minimum. We set x at k plus 1 iteration equal to x at kth iteration plus alpha k d k. Set k equal to k plus 1 and again go to step 1 where you test for convergence. If convergence is achieved, you stop, otherwise you go to step 2. We have presented the convergence rate for a numerical search algorithm when we talked about unidirectional or techniques, optimization techniques for single variable functions. The same definitions apply for multivariable functions as well. So, if I define a ratio which is modulus of x k plus 1 minus x star divided by x k minus x star to the power r, and you take limit k tends to infinity, this value less than p and p lies between 0 and 1, r is greater than 1, then the algorithm we will say that the algorithm is linearly convergent if r is equal to 1. So, look at the expression. In this expression, if r is equal to 1, we call the numerical search algorithm is linearly convergent. Generally, slow convergence is achieved. Here, norm of error decreases by a constant factor at each iteration. Note, in this equation, in this expression, if p is greater than 1, the sequence will diverge instead of converging. So, the p has to lie between 0 and 1. If r equal to 1 and p equal to 0, we get superlinear convergence, usually it is first convergence, and for r equal to 1 and p equal to 1, we get sublinear convergence. If r equal to 2, the method is said to be quadratically convergent, it is first convergence. So, if the initial error is 10 to the power minus 1 and r equal to 2, then the sequence of errors will be 10 to the power minus 1, 10 to the power minus 2, 10 to the power minus 4, 10 to the power minus 8, 10 to the power minus 16, etc. Now, before starting simplex algorithm, let us talk briefly about unidirectional search. We can solve a multivariable optimization problem by successively using unidirectional search technique along a specified search direction. The unidirectional search refers to minimizing a multivariable function along a specified direction by one-dimensional search performed by function value only. So, you can follow the one-dimensional search technique that we have learned in our previous week. Consider minimization of a multivariable function f x in the search direction S I. If x I is the initial starting point, then you need to determine scalar alpha such that f of alpha equal to x I plus alpha S I is minimized. So, the optimal value of alpha star gives the new point along the direction of S I. We need to repeat this process in a new search direction. Now, let us talk about simplex search method. The simplex search method is a very popular search method. In fact, it is one of the most popular direct search method for multivariable functions. It was originally formulated by Spenley, Hext and Hemsworth in 1962. They called it regular sequential search method. What is a simplex? In n dimensions, a regular simplex is a polyhedron composed of n plus 1 equidistant points which form its vertices. So, in 2 dimensions, a simplex will be a regular geometry which will be composed of 2 plus 1, that means 3 points. So, a regular geometry composed of 3 points in 2 dimension is an equilateral triangle. So, a simplex in 2 dimension is equilateral triangle. Similarly, a simplex or a regular simplex in 3 dimension will compose of 3 plus 1 4 points, and it will be a tetrahedron. Now, the property that we use to constitute a search algorithm using simplex is as follows. A new simplex can be formed on any face of the old simplex by projecting any chosen vertex a suitable distance through the centroid of the remaining vertices of the old simplex. The old vertex is replaced by the newly generated projected point. Thus, each new simplex is generated by a single evaluation of the objective function. So, what is meant is, if you have a 2D simplex which is an equilateral triangle, now a new simplex can be formed from this simplex by projecting any chosen vertex a suitable distance. So, let me choose this vertex. So, this vertex will be projected a suitable distance through the centroid. So, let us say this is the centroid. So, along this direction, this vertex will be projected. Now, if I say after getting the new projected point, I want to maintain the regular geometry, that means I still want to get a regular simplex, then I will go through that distance which, when joined by these 2 points, will again give me an equilateral triangle. So, the new simplex is now composed of this point, and this point. So, this point is replaced by this point. So, the philosophy that is used is that if I have a 2-dimensional function, I will get a 2-dimensional simplex. So, I will have 3 vertices. I will evaluate the function values at each of these 3 vertices and look at the worst point. So, project that vertex a suitable distance to the centroid of the remaining 2 and get a new projected point. We call it a reflection, and the worst point in the old simplex is now replaced by the new projected point in the new simplex. Now, I evaluate the function value at the new projected point, and you see that from one simplex, when I go from one simplex to another, I am doing a single function evaluations, except of course, for the first iteration or at the initial stage, initial starting point of the algorithm. So, this diagram schematically shows what we just discussed. Consider a simplex, 2-dimensional simplex. consisting of 3 points 1, 2 and 3. Let us consider I am minimizing a function of 2 variables. So, I take 3 points 1, 2 and 3, I evaluate the function values at each of these 3 points. Let us now consider 1.1 has the highest function value. So, since I am since I am minimizing the function, the point where the function value is highest is the worst point. So, let us consider 1 is the worst point. So, I must replace this point 1 in the new simplex. So, what I do is I project point 1 through the centroid of the remaining 2 points 2 and 3 and go to a distance where again I get the regular simplex. So, that way I obtain point 4. So, I expect that point 4 will have better function value corresponding to point 1. I am minimizing the function. So, the better function value means that at point 4 my function value will be lower than the function value at point 1. So, after doing this, again I compare the function values at point 2, 3 and 4, choose the worst point and extend it through the center of the other 2 points and continue this way. So, now let us put it in formal languages. The function value is evaluated at each of 3 vertices. Consider the worst point. The direction of search is oriented away from this worst point, that means highest value for the function. In the schematic it is point 1. So, the direction of the search is oriented away from this worst point, which is the highest, which has the highest value for the function for minimization problem, through the centroid of the simplex. By making the search direction bisect the line between the other 2 points of the triangle, the direction goes through the centroid. So, when I want to extend point 1 through the centroid of the simplex, I have to draw a line which bisects the line joining points 2 and 3. So, by making the search direction bisect the line between the 2 other points of the triangle, the direction goes through the centroid. A new point is selected in this reflected direction, preserving the geometric shape. So, that is the point 4. If I choose point 4 on the line passing through the centroid, then when I connect 2, 3 and 4, I again get the regular 2-dimensional simplex, that means an equilateral triangle. The objective function value is evaluated at the new point and a new search direction is determined. The method proceeds rejecting one vertex at a time until the simplex straddles the optimum. That means, the optimum point will lie between the 3 vertices of the simplex. That is what we hope will happen at the end of the algorithm. The problem is this, that there may be repetition of the same cycle of simplexes. Now, so if I want to constitute a search algorithm, we require two things. One is generation of a regular simplex given a base point, that means given a starting point, and an appropriate scale factor. Next, we need to know how to calculate the reflected point. So, the first requirement is we must be able to generate a regular simplex given a starting point. So, suppose you have been given a two-dimensional function, you will be given only a starting point, say x1 equal to 0, x2 equal to 0. You have a function of x1 and x2 and you are given x1 equal to 0 and x2 equal to 0 as the starting point. So, to start the algorithm, you have to constitute the initial simplex. So, how do I choose the other two vertices? That means, how do I choose other 2 points given an initial starting point is something that we have to decide first. So, once we can do that, we have 3 vertices, we can form a simplex. At this stage, I would like to mention that you must take care so that these 3 points do not lie on a single line. In that case, you will not form a triangle, because you are going to get 0 volume. All the 3 points, unless the 3 points lie or 3 points do not lie on a single line, you cannot form a triangle joining these 3 points. So, first thing, the resulting, you must get a 0 volume simplex. For that case, if you have a 2 variable function, 3 points must not lie on a same line. If you have a 3-dimensional simplex, that means then the points must not lie on the same plane. So, once you constitute a suitable initial simplex, you can evaluate the function values at the vertices, and then you have to decide how do I get the next point. That means, how do I replace the worst point? We have seen already that the worst point can be replaced by extending the worst point through the centroid of the simplex and then taking a point on that line, so that the geometry is preserved. So, let us see how do I do these two things. So, first, how do I generate the regular simplex? Given an n-dimensional starting point or a base point x 0 and a scale factor say alpha, the other n vertices of the simplex in n dimensions are given by the expressions shown. So, you follow these expressions to get the other n points for an n-dimensional simplex. Note that an n-dimensional simplex will have n plus 1 points. So, you have been given a starting point. So, you still need other n vertices, that means other n points. So, these n points can be generated from the starting point x 0 and a scale factor alpha. You can make use of the equations shown and you can generate the initial simplex. Now, once the initial simplex is generated, you will evaluate the objective functions and then you will replace the worst point. We call that reflection. So, how to calculate the reflected point? So, what you do first is, for n-dimensional simplex you have n plus 1 points. So, evaluate the objective function value at all of these n plus 1 vertices and sort them. So, if I sort such that f of x 1 is less than f of x 2 and f of x n plus 1 is the highest value. So, the worst point is x n plus 1. Now, calculate the center of gravity for remaining n points as 1 by n sigma k equal to 1 to n x k. That means, you sum all the remaining points and divide by n. So, that gives you the center of gravity. Then you replace the worst point x n plus 1 with a point reflected through the centroid x c as x r equal to x n plus 1 plus r into x c minus x n plus 1. Note, in this equation, if r equal to 0, you get x r equal to x n plus 1. That means, you get the original point. If r equal to 1, you get the centroid itself. R equal to 2 will retain the regularity of the simplex as the reflection point will be symmetric. Thus, the new point is obtained as setting r equal to 2, and if you set r equal to 2, you see that you get x r equal to x n plus 1 plus 2 x c minus 2 x n plus 1, which is equal to 2 x c minus x n plus 1. So, if I set r equal to 2 here, I get x r equal to 2 x c minus x n plus 1. That means, the new point, the new projected point or the new reflected point x new is obtained as 2 x c minus x worst. So, now we can propose the algorithm as follows: start with n plus 1 points that define the initial simplex, evaluate the objective function value at each of these points or vertices, sort points x k according to the objective function values such that f of x 1 is less than f of x 2 is less than f of x 3 is to less than f of x 4, so on and so forth, and f of x n plus 1 is the highest. So, consider now the worst point x n plus 1, calculate the center of gravity x c for remaining n points as x c equal to sigma k equal to 1 to n x k divided by n. Replace worst point with a point reflected through the centroid x c and get the new point as x new equal to 2 x c minus x worst. Evaluate the new point. If it is not an improvement, you can consider the next worst point. So, if the worst point when reflected does not improve the function value, we can consider the next worst point in the original simplex, and then we repeat the process. So, how do I terminate the simplex search? When the optimum is approached, the last simplex straddles the optimum point or is very close to the optimum point. We may not get closer to the optimum point if we iterate further, because the simplex then may repeat itself. So, in this case, we need to change the size of the simplex to enforce convergence. We can consider the midpoint of all the sides of the last simplex, and a new simplex composed of the midpoints may be constructed. That means, we can reduce the size of the simplex to half, consider the midpoint of all the sides and then get a regular simplex whose size is half the original simplex. The search is terminated when the simplex becomes small enough or the function values at all the vertices are very close to each other. So, let us now consider a simple example to illustrate the idea. Minimize a two variable function 1 minus x 1 whole square plus 2 minus x 2 whole square. We consider an initial point 0 0 and scale factor alpha equal to 2. We have to generate the initial simplex. So, make use of the definitions of delta 1 and delta 2 given the initial starting point 0 0 and scale factor alpha equal to 2. We have seen how to obtain delta 1 and delta 2 in previous slides. So, once I get delta 1 and delta 2, I can obtain x 1 and x 2, that means other two vertices of the simplex as shown. So, I obtain three vertices. I find out the function values. X 0 at x 0 the function value is 5, at x 1 the function value is 3.0658 and at x 2 the function value is 0.2374. Since I am minimizing the function, x 0 which has the highest function value is the worst point. So, I must replace this worst point. So, I need to reflect this point. So, to get the reflected point, again determine the centroid and obtain the new point as 2 x c minus x 0. We have seen this, that the new point can be obtained as 2 x c minus x worst. So, x 0 is worst. So, the new point x 3 can be obtained as 2 x c minus x worst, which is obtained as 2.4494, 2.4494. Find out the objective function value. The value is 2.3027. The value of the objective function at x 0 was 5, but the value of the objective function at this reflected point is 2.3027. So, this is an improvement because the function value has decreased. So, x 0 is replaced by x 3. If this was not an improvement, we would have considered point x 1 because this is the next to worst point. Since x 3 is an improvement, we accept this. So, the new simplex will consist of x 1, x 2 and x 3. So, the objective function values are listed and we see that x 1 is now the worst point. Note that only one objective function value has been determined, other two are known from the previous iteration. So, x 1 is the worst point. So, we need to reflect x 1 and we continue as shown. With this, we stop our discussion on simplex search, lecture 27, and in the next lecture, we will talk about improvement of this simplex search method and we will present the algorithm for Nelder-Mead simplex search method, which is bit complex, but more efficient way of doing multivariable search.